Hello everyone, welcome back to the lecture. We want to continue the data mining topic today. Last time we talked about gradient descent, which was a numerical approach to find or optimize a model like linear regression or logistic regression. Today I'm going to talk about stochastic gradient descent. The name is a little bit more scary, but it is actually easier and simpler than gradient descent. So a little bit of a reminder. So what was gradient descent? Gradient descent was used to find the minimum of a loss function, right? So that it gives us the best parameters. But we couldn't solve it mathematically and directly, so we use a numerical approach. So the idea was that we would start, this would be the loss function, right? And we start from a random point, and the idea was that in every step, we take a step towards the steepest direction, right? So we would calculate the gradient or the derivative and find the steepest slope, and we move towards that direction, and we repeat this process in a hope to find the minimum. But it has some problems, and that's why people came up with the stochastic gradient descent, especially when we have a lot of data. So this was the lovely formula for gradient descent, right? So quick recap. So this was the loss function. We would take the derivative, right? And the loss function takes two parameters. One is our estimate. So if we have an email like xi, we would pass it to this function, our model, to tell us if it's a spam or not a spam. And we would compare that with yi, which is ground truth, right? So if we have a match, there's no loss to score. If there's a discrepancy between what we estimated and what ground truth is, we would get some scores, which is bad, right? So we would add up all of these scores for all of the training items, right? So these are all of the emails I have. For example, n can be 1 million if I have 1 million emails to train on. And then this would be an iterative algorithm, right? We have our current weight, which is our current position on that curve, right? And we use this to move to the next step. Now, the main issue is that sigma. We want to get rid of it, right? Because if we have like 1 terabyte of data, in every iteration of this algorithm, we have to read all of that data, right? Because this, in order to calculate the sigma, we have to go from 0 to n, right? And if we have like 100 iterations, we have to read our data 100 times, which is really bad in big data, right? So people came up with stochastic gradient descent, or SGD. As you can see, it's exactly the same as gradient descent, except that we got rid of that problematic sigma. It's exactly the same, right? We had a sigma, I was the index, so that's why we had xi, yi. We got rid of the sigma, and this becomes x and y. What does it mean? It means that in every step, we only calculate this based on one data point. Previously, in gradient descent, we would look at all of the data points, right? We would calculate the loss for all data points. But here, we only use a random point in every iteration. You may say, wait a second, this should be problematic, right? We only look at one point at every iteration. Yes, but surprisingly, it works really good. So why don't we use a random sample? We use a random sample. So we actually use a random sample, right? So I'll tell you how we actually process the points. But what you need to know at this time is that we look at a random instance in every iteration. So I read one of the emails I have in my training set, and I calculate it based on that. Okay, only 1 point. That's why this one, what happened? The gradient descent batch processing, because I need all of my points in every iteration. But this one is online, right? Meaning that I can process some data points and then I give you one more data point and you can just do another step based on that new data point. So you can do online processing. As the points arrive, you can basically keep training your model, right? Give you more emails, you can keep training it, right? But in gradient descent, you say, no, wait a second. In every iteration, I need all of the emails, right? I cannot work like that, right? It's batch processing versus online processing. So batch gradient descent and a stochastic gradient descent are two ends of the spectrum. There is something in between called mini batching as well. This is basically, instead of looking at a random instance, it looks at a random subset of instances in every iteration. So it's somewhere in between, okay? So in every iteration, we look at 10 points, for example, 10 emails, right? And then we go to the next iteration, we look at 10 other emails. So like something like that. So so that was a stochastic gradient descent, okay? Is there any question about it? Because I want to explain another concept, and then I will explain how these two concepts join together to solve the problem. And the original problem was that in gradient descent, the sigma requires all of the data in every iteration, which is really heavy processing. Everybody's happy with stochastic gradient descent. So as you saw, it was actually easier, right? We look at 1 point. So the second concept is ensembles, okay, or ensemble learning. What is that? In ensemble learning, we train multiple models. Okay, until now, whenever we talked about training model, we were talking about a single model, but here it says multiple models. And now, but what happens if I train multiple models? So for example, if I train 4 models, and then this is for spam detection, for example, 3 of them say it's a spam, 1 of them says it's not a spam. Oh, okay, so we need also a technique to combine the outputs, right, in this approach. And another detail we should remember is that these models should be independent. Otherwise, it's not very useful. So one common way of implementing ensemble learning is that we partition our data, okay? And so, for example, we divide the data into 4 chunks, right? And then we train a model on each chunk of data. It can be the same model, okay? For example, we have a logistic regression. So I've divided my data into 4 chunks. I apply logistic regression. I train a model based on logistic regression. On each chunk of data, I end up with 4 models, right? That's the idea. And then obviously I need to combine, because if I have multiple models, each of them says something different. So I need to combine. One common technique to combine is majority voting, right? So if 3 models are saying it's a spam, one says it's not a spam, we probably go with spam, right? Majority wins. Sometimes it's not a binary thing, it's more like a continuous output, such as linear regression, right? One model says 1.2, another model says 1.5, another one says 1.3. We can take the average of these models. So typically majority voting or averaging. Why does it work? The idea behind it is that if we have some errors, okay, it is unlikely that all of these models that we have suffer from that error at the same time, because they're independent, right? So if one of them or a few of them make a mistake, it's unlikely that the rest of them also make mistakes, right? That's the whole idea behind majority voting. We trust the majority of models. We say, okay, some of them are saying something different, but I'm going to ignore it, assuming that the errors are not correlated and the majority is correct. Obviously, it's not the case all the time, but in practice, different experiments have shown that this technique works really nicely. So you have a meme about, you can see many of these concepts are really basic, right? Having multiple models and just do a majority voting, things like that. Again, fancy names for some basic stuffs. Let's move on to map reduce implementation of all of these things. So we talked about the stochastic gradient descent. I talked about ensemble learning. I want to combine them now, and I want to show you a very interesting implementation of them in MapReduce. But before we do that, let's remind ourselves what we learned last time. So we have gradient descent. The idea there was that, okay, in every iteration, we need to calculate the sigma is too much work, right? So we can basically divide the data and ask multiple mappers, right, to calculate part of the sigma, right? And then they would they would send this partial sum to a reducer that adds up all of these numbers and calculates sigma, and it can update the model then. And remember, this was only one step, right? So we had to iterate in order to find the minimum, right? So that was the idea. You may say, is this ensemble learning because you divide your data? No, no. In ensemble learning, we divide the data and we train a model on each chunk of the data independently. But I'm not doing that, right? These mappers are just helping each other to calculate the sigma, right? All of them are working towards training a single model. So this is not ensemble learning, right? This is what we had last time. Now I want to show you how we can implement ensemble learning. So this is the interesting part here. Previously, let me go back. So when this mapper reads all of the data that it was assigned to it, what was it doing? It was calculating part of this sigma here, right? So when it reads reads one instance from the trace, what does it do? It would be one of these i's, right? One iteration of the sigma, right? It calculates one of this, and then reads the next one, adds it to the next one, so on and so forth, right? But in a stochastic gradient descent, I don't have the sigma, right? So when I process a point, that is one step on its own, right? I can go to the next step. Do you agree? Because I don't have a sigma. So technically somewhere a loop goes away, right? So every time you process a point, you have done one step. It takes you to the next step. Interesting. So this should simplify things significantly. Now, if I divide my data into 4 chunks, I can train an independent model on that chunk of data using the ensemble learning idea and stochastic gradient descent. So you have given me some of the emails, right? Do you agree that I can train a model on that chunk of data independently? Sure, right? What I do, I read the first email, right? It takes me to the second step. I read the second email, it will be this third step. So when I'm done reading all of the data that was assigned to me, I'm done, right? I've processed all of the data points using the stochastic gradient descent. So that point that I am right now is the minimum, basically, right? I've converged, it's done. So that's a model, right? It's like, and then the next guy does the same thing independently, Remember, what's the difference? Previously, when I read my data in gradient descent, that would be part of the sigma. I had to just send it to a reducer so that with the help of other mappers, we could calculate the sigma in one step, right? Now, when I read all of the data that's assigned to me, I'm done, right? Because that loop goes away. So I end up with 4 models. So this is a stochastic gradient descent plus ensemble learning. Very simple, right? Is there any question about this? By the way, your next assignment for both 431 and 451 will be on this. So make sure that you understand this concept. So you will train a model using a stochastic gradient descent. All right, so this idea has another minor version, okay? It doesn't help that much, but just that you have seen it. So again, before I move on, I emphasize that there's no iteration here, right? When we read the data, we're done, right? We had iteration because previously we could only process one step, so we had to go to the next step, but here we are done. Umaid, go ahead.
Yeah, so but for gradient descent, we need to iterate it like again to reach the minimum point. So we don't need to do that anymore? Or?
So we are iterating here, right? So by reading data, right? So every time I read one of the instances, one of the emails, it's one iteration of the algorithm, right? Because here, what do I need to process in one step? Only one data point, X and Y, right?
Yeah.
So it takes, but previously it was not the case, right? There was a sigma here, right?
Yep. So in mini batch, then we would go back to the original implementation if there is a mini batch stochastic.
If you want to implement mini batch, it would be you could still, I think, implement it like this, okay? Because you don't need all of the data, right? You need a subset of the data, right?
Yeah.
The issue with gradient descent is that in every step you need all of the data, right? So me as one of the mappers cannot just do something on my own, right? We need the data that other guys are processing, right?
I see.
But here it's a subset of the data. So I can still do the same thing, except instead of going to the next step after reading 1 point, I can go to the next step after reading 5 data points, for example.
I see. Thanks.
Yeah. Good question. Now, the variation of this idea, wait, do you have another question, or this is? So it looks like there's a problem with the raise hand thing. So the variation of this is that you can use reducers if you want, okay? I don't personally like this approach, all right? I don't think you have much gain using this idea. What's the idea here? The idea here is that mappers, instead of basically calculate or updating a model, they just calculate this part, okay? The step, the basically movement part, right? They calculate that and they pass it to reducers, okay? And then we can have multiple reducers here, and then they would take these values, right? And they just update the model, right? So, and then the number of models will be the number of reducers that you do, because updating the model actually happens in reducers. I don't like it that much because mappers don't do much, right? So this may actually hurt your performance, but it's a possibility, right? That you can train a model in the reducer. Makes sense? The major one is the one we had in the previous slide. This is a variation, might be useful in some cases. All right, so some other details about this. How do we store the model? You can output it as site data because it's not big data, right? It's just the parameters of the model. So you can output this as site data, or you can emit it as intermediate, like Hadoop, for example. Data, doesn't matter. Both of them work. Now, how about the Spark? So okay, we have a good idea about how to do this in Hadoop, is there anything specific to Spark that we can use? Yes. CS431 students, you will directly need this for your next assignment. So let me give you an example. There's a new transformation that you probably haven't seen, map partitions, okay, that will be very useful for implementing this idea. So if we have an RDD, right, that has some partitions, right, let's say 3 partitions, right, and you know that we have items or lines in every partition, right? What happens when you apply map? Do you agree that you specify a function, right, and that function is applied to every line? So the resulting RDD will have the same number of partitions, right? Spark would read the first line or first item, applies the function, and adds it to the new RDD. Reads the second line, applies the function, and write it here, right? So basically, if I have 1 million items in the source RDD, that function I apply in map is applied 1 million times on every item, right? And it gives me a new RDD, right? Now, in ensemble learning, we want to basically apply something to every partition, right? So basically, the partitions that we have in my RDD can be my basically division of the data, and I want to train a model on every partition of the RDD, for example. But I cannot use map. Map is applied to every item, right? I want something that's applied to every partition, right? So when you apply map partition, something interesting happens. When you call map partition, it's called per partition. So if I have 3 partitions, it's called 3 times, okay? And what happens is that you have to specify a function like map, but the difference is that in map, that function is applied to every item, but here, that function is applied to the whole partition, right? But you may say, okay, if it's a partition, how do I get access to the items inside the partition? Spark provides a pointer to it. So it's an iterator. It gives you an iterator, right? So still the output will have 3 partitions, right? But instead of the Spark applying it to every item, right, it applies it to whole partition, right? It says, hey, give me a function and I apply it to that partition. So you can implement your stochastic gradient descent in that function, right? And then it gives you an iterator, right? So you can loop through the data points, and in every iteration of that loop, and this is like a Python or Scala loop, right? You can basically update your model, right? Every time you read an email or a data point, you calculate this, you go to the next step, and you're done at the end. So then you can write it out. I don't know, this will contain your model, for example, here at the end. So that's the idea. So we need to work with this and write some simple programs to get a better sense of how map partitions work. So what I just explained is implementing these techniques, right? Such as the stochastic gradient descent. Do we do that in practice? Not really. There are libraries that we use, okay? And specifically, if you use Spark, there's this Spark ML extension that already provides many of the things that, or probably all of the things that I talked about today or last time. For example, it has this linear regression with the stochastic gradient descent. Okay, you don't implement it, you just call it, okay? It has a dot train function, and you pass your data, and it gives you an RDD, which is your model, 1 line. And then you can use that model to predict or to either to test the accuracy of your model or just to use it to predict new stuffs. And then you take your model, it will model that predict and some new data points, and it gives you predictions. So in a few lines of code, you do this. But in this course, we try to understand how they work, right? So that we understand when should we use what, and we have a better understanding of what's happening behind the scene. Unfortunately, in practice, there are many data scientists that use these tools without having any idea what they are. It's true, right? It's really bad. That's why some people just try different things. They apply this, doesn't work, they apply something else, see if it works or not. So it's just brute force instead of understanding, okay, this is how this works, I should use this one, right? Not everybody, but some people. So let me give you an example of some of the things that we talked about. So this is a sentiment analysis case study. So what we want to do is basically we want to do binary polarity classification. So we have some tweets. We want to do sentiment analysis. We want to see if they are positive or negative. Okay. The data that we have is 500,000 positive, 500,000 negative tweets, okay? And we basically train on different subsets of of this data. Sorry. So 5K I explain is the test data, okay? So it's like half-half, so that we are not biased toward negative or positive, okay? And training happens on 1 million, 10 million, and 100 million tweets. And the feature they used was a sliding window for byte foreground. So they would take the bytes and they basically slide a window over these bytes. Okay, and every 4 byte would be 4 gram. So the feature would be, do we have that 4 gram or we don't have that 4 gram? And they would slide that over the data. Okay. And the model and optimization they use the logistic regression for the model, and they use a stochastic gradient descent for optimization. Now we know all of these things, okay? And they also use ensemble learning of different sizes. I will explain the results. So here, we don't have any ensemble learning, okay? This is just the logistic regression plus the stochastic gradient descent. So we have the light, I don't know, it's gray or white, and then light gray and dark gray, okay? And this is basically different sizes of the training set. So 1 million, 10 million, and 100 million. And we have seen this before, right? As we increase the size of the input, typically the accuracy improves, and we see this. Now let's use ensembles, right? So this what you see here is the number of ensembles we used, okay? And you can see something very interesting. All of a sudden, the accuracy jumps significantly. And the interesting thing is that the results I'm showing here in the middle, these are for 10 million instances. And the interesting thing is that they beat this one, right? The 100 million instances. So actually having ensemble learning with 10 million is giving us better results than not using ensembles and 100 million. That's interesting. But if you also use ensemble learning on the 100 million instances, it gives you a little bit more accuracy, but we don't gain a lot per se, okay? But it improves a little bit. So the idea here, what you need to learn here is that you see how much ensemble learning can help to improve the accuracy, okay? All right, Mark, go ahead.
Yeah, Professor. Hey, just about the last slide. Why should this work in theory? Is it simply because like each of the classifiers, like as you mentioned before, like if there's happens to be some kind of bias in one of the partitions of data, like the rest of the classifiers will overcome that and vote against that, or why? This seems to me like a very surprising result. I was just wondering, like, why this should be the case.
The way that I understand this is that if there's some sort of problem in the training data. When you train one model, that problem infects that model, right? But when you use ensemble learning, that problem probably affects some of the models and not all of them. The hope is that the majority of the models were not affected. That's why when I take majority voting, those problematic models will be overwritten by the good ones.
Got it. And this is still assuming that the data is completely randomly distributed across the classifiers, right?
Yeah.
Cool. Thanks.
No problem. It's pretty amazing why it works, because the same data, right? We just partitioning and train multiple models on it. We didn't use more data, so that's interesting. So good question. So if you remember, we said supervised machine learning has two main steps: training, right, and then testing and development. Let's talk about testing a little bit. So we want to evaluate how well we are doing. If you remember, this was the idea that we had, so that we wanted to find a function f that actually, and we actually had this restriction, so we wanted to optimize it, right? Now, if I've already done this, why isn't this enough if I have used mathematical optimization to find the best function? Why do I still need to evaluate it? Any ideas? Isn't this optimized? Great. Okay, I got a few answers. All of them are correct. Yes, you optimized, but you optimized for your training data. That's not all of the data in the world, right? What if we don't know what happens if we apply this model on some unseen data? Memory overflow was a good attempt, but didn't work in this case. So the idea is that, okay, you have your training data, you train a model, but there are tons of unseen data, right? Machine learning, machines don't learn anything, right? We know that. Don't tell anyone else. They look at some training data, they find patterns in that training data, right? And then they try to see if that pattern is found on some unseen data. If that's the case, we can classify them. But it's totally possible that the unseen data has different patterns that we haven't seen yet, right? So that's why we need some sort of end-to-end metric. So we need some sort of accuracy, right? But unfortunately, accuracy is not enough. Why? Here's an example. You asked me to develop an email spam detection system, okay? I designed something that flags every email as spam. So I can claim that I have accurately found all of the spam emails. My accuracy is 100%. No? So it's more complicated than that. And that's why we have different metrics and not just a single metric, okay? So this is really interesting, and it will be useful later in your work, in your final project. So we have two possibilities for ground truth, right? So either, and let's think of like a spam classifier. Either it's a spam, positive, for example, or negative, right? Think of binary classification. And then prediction has two outcomes, negative, positive, right? My prediction says either the email is a spam or not a spam. Now, these two possibilities for each create four possibilities, right? 2 times 2. How? For example, This case is good, true positive. The email is a spam, and I detected it to be spam. Good, that's called true positive, right? It was something, and we said it's that thing, okay? True positive. Then we have false positive. It was not a spam, but I said it is a spam. That's false positive, right? And then we have false negative. False negative, meaning that we said it's not spam, but it was not true. So it's a false negative. We said negative, but it was a wrong negative. So false negative. And finally, we have true negative, which is good again, which was the case that it was not a spam, and we said it's not a spam, right? So actual was negative, predicted was negative, so it's true negative. So out of these four, true positive and true negative are good, okay? False positive, false negative are bad, right? Because it's a mismatch between reality and what we predicted. Makes sense? Now, using these metrics, right? For example, you can count. You can count, for example, out of, I have like 1,000 emails for testing, right? Then you can count how many true positives I had, how many false positives I had, how many false negative and true negative I had, right? Using those values, we can calculate some other metrics that are very useful. The first one is precision. Precision is basically how accurate you are in detecting something, right? So for example, when you say something is a spam, how likely it is that you are right. So if precision is 90%, it means that when you say something is a spam, there's a 90% chance that it is a spam. That's the definition of precision. But it doesn't tell me about how many of the spam emails I found, right? There might be 100 spam emails and I only found 10 of them, but I was accurate, right? For example, I correctly said all of them were spam, so my precision is 100%. But is that a good algorithm? No, because probably it's too conservative, right? It only says something is a spam when it's almost sure that it's a spam. And the problem with that is that it couldn't detect many of the spams, right? High precision, but bad recall. And that's the other metric that we have. Recall tells you what percentage of the things, like for example, the spam emails, you could identify, right? So if there are 10 spam emails, sorry, if there are 100 spam emails, but I found 10 of them only, my recall would be 10% only, right? If I set all of them correctly, my precision can be 100%, right? But my recall was bad. On the other end of the spectrum, I can say everything is a spam, right? Then I correctly find all of the spam emails, so my recall is 100, but my precision will be really bad, right? So you can see that there is typically a trade-off between precision and recall, right? It's typically about how aggressive the algorithm is about detecting something. And there are some other metrics as well. There are other names for some of these. So we have type 1 error, which is false positive. False positive is type 1. It's when you tell a dude that he's pregnant. Okay, it's false positive, right? We said it's positive, so he's pregnant, but it's false. It was wrong. It's false positive. This is type 1 error. We also have type 2 error. That's false negative. That's when we say no, but it's wrong. False negative. That's the case of telling a pregnant woman she's not pregnant, right? It's a false negative. We said no, and it was wrong. That's type 2 error. So now that takes us to ROC and PR, which is precision recall curve. Let me explain these. You need these in your next assignment. We have already developed a program that calculates it, so you don't need to worry. You just train something, and then you use our program to calculate ROC. What is ROC? So ROC is the plot of false positive rate versus true positive rate. False positive versus true positive. There is one corner of this plot which is the best. So we have 4 corners, and I have a poll for you, so I will launch it in a second. So we have 4 corners in this plot. Which one is the best? Let me launch a poll quickly and tell me which one is the best. Launch. There you go. So this is false positive versus true positive. Okay, so I got 17 responses until now. Most of them, 94%, said D, and that's correct because the x-axis is false positive, so it's bad. Okay, so this corner is, so here is better on the x-axis, and then on the y-axis, true positive rate, so it's good, right? So whenever it starts with true, that's good. Whenever it starts with false, it's bad. So it's true. So this corner is best. So this corner is best. So when you plot false positive versus true positive, it's best to be close to that corner. Okay. Ideally, the line would look like this. Right? It goes to that corner. So in order to compare 2 lines, because it's difficult, right? Sometimes this line is closer, sometimes the other line is closer. So we typically look at the area on their curve, right? So if one algorithm has a better, so when you're comparing 2 different algorithms, you look at the area on their curve, and the one with the higher value performs better. That's the idea. So the area under curve for the red line that I drew, which is the ideal case, is 1, right? Now, the second plot that you commonly see in research papers that predict something is a recall precision or precision recall plot. It basically plot these 2. So both of them are positive. So this corner is the best for this curve, right? Here is the best. And you can just see which line is closer. So when I compare algorithm 1 and 2, it looks like in general algorithm 2 is performing a little bit better because it's closer to that line. Okay, so again, ideally the line is like this. All right, is there any questions about these plots? All right. So how do we do training and testing? So we have some data set, right? We split the data set into training and testing. Usually we give most of the data to training, and then we test on some part with like 20-25% of the data. So what do we do? Before I move on, Mark, go ahead.
Hey, Professor. Just had another question on the plots from the slide before. Maybe this is obvious. What is exactly being varied in order to create these plots?
Okay.
Is there like a parameter that creates like a trade-off?
Yeah, thanks. That's a very good question. Why do we have a line? Because if you run an algorithm, that's a point, right? Because it gives you a particular precision and a particular recall. So it would be 1 point, right? So it depends. One possibility or the way of generating such plots is that we tune a parameter. Okay, so there's a parameter, for example, that says how aggressive we detect things as being a spam, right? And then we change that and we can get a plot like this. All right. Training. So going back to that question, for example, when you do this in your assignment, you end up with one number. So yeah, it depends. I mean, if you, I think, yeah, that's what I think is, that's just, sorry, that you get the area under curve, I believe, in the assignment, that would be one, just one point. So so again, so we divide the data into training and testing. And what we do in training is basically finding that argmin and the stochastic gradient descent and all of the things that we talked about. How do we test? We basically apply the data that hasn't been seen to the model, and we calculate precision and recall and things like that. So that's basically. Sometimes we don't have enough data, right? How can we improve our testing? A trick that can be used is cross-validation. What does that mean? It means that, okay, first you divide your data like this. You train on the green part and test on the pink part, okay? Then, okay, that gives you like precision recall, right? And then you can choose another part of the data to be your testing set, right? So now 1, 2, 3, and 5 are training, and 4 is testing. So you can just change what partition of the data is used for testing, and this is called cross-validation. So in practice, we train, we test, and sometimes we skip cross-validation because we don't have enough time, and we move on to other types of testing, such as A/B testing. What is A/B testing? It's basically having a group for treatment and the rest for control. So for example, if Amazon wants to test something, they will allocate a small percentage of their customers, let's say 1%, to test a new recommender system. And the rest of the users, the 99%, still use the old system, okay? And then after a while, they compare the two to see, could they increase the sale or not, right? Is the new recommender system on the treatment group working better? So they can compare. Why do we have the control group? Because something can change, right? So you need the control so that if you see a difference, you can say that, yeah, it's because of the algorithm and not because of something else, right? Because if I just deploy a new recommender right now, and I conclude that, yeah, sales went up significantly during the month of November, it's because of my better recommender system, right? That's probably wrong. It's because of the holiday season, right? That's why we need a control group. It's pretty complicated, actually, right? How do you partition users, right? So that the treatment group is not a special group, right? The novelty is an issue. Sometimes you'll see that, yeah, we saw improvement. It was really because it was something new, not necessarily better, right? Because you changed the UI and that change had some effect just because you changed it, not because it was better. And there's so many other complications, such as short-term and long-term effects, learning effects, right? Sometimes you use it, for example, you design a new UI, you test it, and you'll see that, yeah, it's working better for users. But if you give it time, you will see that your performance goes back to what it was before. So it's like the learning effect issue. And sometimes there are also funny stuff, such as a nosy tech journalist, because when you do A/B testing, you release what you're testing to some of the users, right? For example, if Amazon wants to test a new UI, if they do that, some users will see the new UI, right? So sometimes it can leak a company's secrets. All right. The rest of this lecture is going to have a little bit of a different tone. It will be more fun stuff. Okay, so that's good news. Okay, that was what we taught you. Okay, that's what we have to do, right? All of the classical stuffs. But now I'm going to talk about what happens in reality and in practice. Okay, and it has a funny tone. So, okay, machine learning in academia and also true for other fields, unfortunately. So what we do is usually we download an interesting data set, okay? We run some baseline model as our reference, and then we try to come up with a better model and we build it. And then we ask ourselves, is this a better model than the baseline? If yes, we publish the paper. Otherwise, we try again until we can find a better model. So the scientific method of doing science is the top flowchart. So we observe a natural phenomena, we formulate a hypothesis, we test the hypothesis, we typically modify it, right? And we every time we do rigorous experiments, and finally we establish a theory. In reality, things are a little bit different. First, we make up theory based on what funding agency wants. Or if you work for a company, you are told what to do. So we design a minimum experiment that suggests the theory is true, and we go ahead and publish a paper on it, right? We just modify, instead of the iterative modifying the hypothesis, just modify the theory to fit the data. And we go ahead and publish the paper, and we defend the theory despite all of the problems that it has. And here's a relevant meme for you. It's about adjusting the data, right? So I found out why you guys enrolled in this course. And the waiting list is so big. So let's see, again, let's compare fantasy and reality. Okay, from what I taught you, you may think, okay, extracting features is interesting. We talked about this last time. Then we developed cool machine learning techniques. We learned about some of those today. And hopefully at the end, we make some profit. So all of this is really nice. In reality, things are again a little bit different. Typically, you are told what to do, okay? So, or sometimes it's not really clear what the task is. So we need to find that out. Then we need to find out where the data is, right? So we need to ask people to figure out where you can find the data. Then you have to spend time to find out what's in the data set, because they are typically not well documented, okay? And really, there will be tough time trying to figure out what this is really. And then you clean the data, because traces and data sets are just full of garbage, right? Or things that you simply don't need, right? So you need to clean the data. You need to prepare the format for what you want to do next. And then you can extract features. Why do you put this sad face right beside it? It's exactly like fantasy. I'll get back to that. And then you do machine learning, okay? As I said, just train, test instead of developing cool machine learning techniques. Then we fail after all of these things, right? And then we have to iterate. So very little of data science is about machine learning per se. It's all about cleaning the data and dealing with all of these problems. And projects will be released soon, and you will do all of these things on your own. Let's have another meme. Why not? So about what people think about data scientists. Do you know what the funniest thing is? What I think I do is exactly like my slides. All right. So you will probably hear this a lot, that a lot of data science is about cleaning the data, right? You will be surprised how much time you will spend on cleaning the data and figuring things out, right? Because of different terminologies. Like in one company, terminologies may change over time, or when you switch to another company. I reset my video. I realize it's very blurry. You will see that they use different terminology, right? So it takes time to understand what is what. And then you're probably familiar with this, right? Well, we have camel case for naming variables and functions. We have a small camel case. We have snake case with underscore. We have camel snake with underscore and capital. We have dunder snake with 2 underscores. So, for example, a simple variable can be called different things. It makes it a bit difficult to understand what is what. On feature extraction, I told you I will get back to this. This was the only thing that was shared between fantasy and reality. So you think feature extraction is fun? Well, this is an example of feature extraction at Twitter. So maybe that's not that fun either. You may say, all of these things are small things, right? Are they really important? The issue is that they accumulate, right? So there are small things, but you have to deal with so many of these small things that like 2 months pass and you realize you haven't done anything yet, right? So that's the issue. So on feature extraction, in the next assignment, we will give you a few of these and you have to figure out what they do, and then you will develop one of your own. Did I scare you? Because that was the goal. Happy Halloween. I'm joking. We are not going to give you those things to figure out what they are. Okay, I won't see you until after Halloween, so I thought I have a slide on it. This is a conversation between a front-end engineer and a data scientist, and these things really happen, right? So the front-end engineer developed a new feature that logs clicks, right? Where and when users click, so that we can basically develop different machine learning techniques on them. So first, the data scientist asks, where's the data? And then the front-end engineer says, oh, we stored it on those servers, right? And so, okay, that was kind of non-intuitive, but okay. And then yeah, the data wouldn't fit, so we had to shoehorn. And then a week passes, and the data scientist looks at the data, cannot find the timestamp on the clicks, right? Because we need to know when the user clicks on something, right? So where is the timestamp? And the front-end engineer says, hang on, I don't remember. Said, oh, bad news. It looks like we forgot to log it, actually. So the data scientist would be grumble, grumble, grumble. So these things really happen in practice. So, so we do all of these things, and it finally works. So good news, you're halfway there, or bad news. There are some other things that we need to take care of. Does it actually work? That is a good question, right? We develop something and we test it on some data. But does it actually work in practice, right? We need to do A/B testing to be sure. And the other interesting thing is it fast enough? You may come up with this excellent idea for a recommender system, right? But it takes 2 years to run on Amazon data. It's no good, right? So it must be fast. Okay, 2/3 there. And finally, moving something to production is a very different story, right? What are your job dependencies, right? Because when you want to deploy something on production servers, we need to know about all of these things, right? How and when do you want to schedule your job? It's typically these machine learning techniques are like you want to run it every day, every hour, right? How do you want to schedule it? Are there enough resources, right? Because your algorithm cannot kill the server, right? These are production servers. So how much resources do you need? How do you know if it's actually working? It's very difficult, right? When you deploy it at a big scale, figuring out and tracking how well it's working, if it's working at all, it's actually very difficult. How do you know when it stops working, right? So infrastructure is very critical. So a lot of plumbing. So the takeaway lesson for this lecture, the second half, is that most of data science isn't really glamorous, right? It's a lot of data cleaning. And if you didn't have an experience, you will have one for your final project this term. All right, that's the end. Questions? Let me stop recording. We'll be around a few more minutes.